Okay, testing. Last presentation of the day. So if I were really annoying, I'd ask you to stand up and stretch and do all that stuff that my math professor used to do at the university. But I will settle for a mental stretch. Good to see. My name is Niklas Norin, and I work for a company called Disruptive Technologies. How many embedded programmers do we have here today? 1, 2, kind of. How many back-end programmers? A few. How many front-end programmers? UX? Awesome. This is going to be a little bit of a mix of all of those things, so hopefully it will keep your attention. So, a little bit about myself. My background is from Texas Instruments, where I used to work at the Oslo office, which is the wireless division. I worked as an embedded programmer, but I've now been with Disruptive for a few years. And what have I done at Disruptive? Well, I started doing assembly programming inside this little microcontroller, inside this microcontroller. This is like the equivalent of starting in the mailroom, basically. It only goes up from there. So when I got to start using C, I was, super happy. It's kind of like being able to write code with letters again. And eventually I transitioned into coding some Python and some Golang as well, both on embedded devices and a little bit in the cloud. But now I work mainly with the developers that want to integrate with our products. So one thing is I really love hard questions. So if you could do me like one favor, it would be if you have a question, write it down on your phone, and I promise you'll get an opportunity to ask me after the talk, either on the Q&A or just over a beer later. Seriously, like hardest question wins something. So when I've been working with our developers, I've also actually taken on some responsibility for customer support. And something I've learned about when I'm working with customer support is, well, it's really gotten me a new angle at the user experience. And I realized that there's really only two types of user experiences when it comes to support. And either it's really awesome or it's super crappy. I mean, it's easy to imagine. Let's say that you're stranded on an airport in Southeast Asia, and your flight has just been canceled, and you're looking for a way to get home. You call up the airline, you're sweaty, you're exhausted, you just want to get home to your family. Chances are that by the end of that phone call, you're either super angry or pretty impressed. Either way, it will show in your Facebook post later that day. And I'm also really noticed when working with this that user experience and working with our products and working with our developers, that user experience is a little bit like acceleration. You're really good at noticing a change, a positive or a negative change, but you get used to a constant experience really quickly. And what I mean by that is that when you're experiencing a positive change in user experience, like something is way better than you anticipated, you get this feeling of flow. You get this feeling of, I don't know, somewhere between giddiness and awe. I don't know, it's like someone found this objective way that something should work. This intrinsic way how this user experience is supposed to be, wrapped it in gold wrapping paper and gave it for you to unwrap. And as a developer, I'm talking about a really well-designed command line interface. I'm talking about a really beautiful, intuitive API. But even outside the developer role, I'm talking about going through US immigrations and being able to use the touchscreen interface instead of the super grumpy immigration officer interface. And you take notice, and this is something that you tell your friends about. And another really important thing is that when you're experiencing an improvement in user experience, you also get used to it and you expect the same level of user experience in the future. And it's very similar with negative user experience. So you're experiencing something that's way worse than you thought it would be. And when this happens, you kind of cringe. It's as if you're listening to your favorite song that you know by heart, but it's played by this really crappy cover band. You kind of understand what they're trying to do, but you also wish that they hadn't tried it in the first place. And I'm talking about, you know, you're going up to a screen, and there's a button on the screen, and you press it, and you realize it's not a touchscreen. Or when you go into an elevator and there's tons and tons of floors, you want to go to the reception, but the reception button isn't in another color and it's not protruding anything. And I'm talking about you're super excited about this new web service or this website you want to use, so you register a new account, and then it takes 10 minutes for you to get the confirmation email so you can log in. Again, you take notice and you tell your friends. And the thing is that the thing about changing user experience too is it a little bit like leverage, because not only are you experiencing someone that's maybe a little bit better than what something was before, you're also comparing it to a competitor which now looks a little bit worse than he did before. So it's a little bit like leverage, and we really notice these kinds of change. But what I find the most interesting is when we experience the same user experience and we don't have the same reaction. And what's really interesting about this is that once you've experienced something and you've heightened your expectation, and then someone else spend the same amount of effort to create the same kind of user experience to the same kind of high level. But I guess it's just human nature that you get used to this really quickly and you don't appreciate it. Like, if you've experienced the touchscreen immigration, you know, officer, then in the US, and you also discovered the same. It works the same way in Canada and Japan and other countries. You know, you don't really appreciate this as much. You might not tweet about it the third time. And one thing I noticed here is that it's actually about 7 years ago. I was going to buy a new phone. I just remember this the other day. And I went to the store, and the sales guy, he knew everything about the resolution of the screen, how many gigabytes of storage it had, and so on. But do you think he had an answer when I asked him, what phone should I buy if I want the best call quality? He had no idea. And he's selling phones. So the thing is, it seems like when UX is at a certain level, then it's only like the condensers that really appreciate any increase. The average human being doesn't, and find other things to focus on. And of course, this year, it was 7 years ago, I think that cell phone cameras were starting to get into like the couple of megapixels. And that was a lot then, and storage and screen resolution was really lagging behind. So of course, that's an area where we could see a lot of improvement, so it got a lot of focus. So what's the big changes that I think that we're seeing in user experience today? Well, it's really about the experience that it's not only on the screen. And if you're designing an experience outside the screen, you're kind of limited in what you have as of user input. And when it comes to kind of the ultimate user experience outside the screen, I often think about what Amazon is trying to do at the moment, where you can walk into a grocery store, you can browse the greens, you can look at all of the different brands of syrup. In the US, they have like hundreds. And then you can pick the one you want, and you can just walk out the door. And you will get the receipt in your pocket. You know you'll get the receipt in your pocket. And so how do they do this? With tons and tons of sensors. So we designed this little sensor here. It's about the size of the keyboard button on your laptop, and it weighs about 2 grams, and it's so thin that it can fit in the crack of a door. It can last about 15 years on one battery, and to put that into perspective, if I install it here at NDC today, you wouldn't have to replace this temperature sensor until 2033. It's also completely wireless. We've measured actual range. We've measured about 1 kilometer of range. And I always find it fascinating to put that into perspective, because you can't fit a lot of antenna into this little thing, and it's 50,000 times the width of the sensor. So it's pretty cool. We're going to market with 3 different sensors, and it's going to be one temperature sensor, which can be used from down to freezer temperatures to up to, greenhouse temperatures. We're also releasing a push button, which can be used as, well, your imagination. Refill soap, call a cab. Set a reminder to call your mom. It can be used to anything that has to, call to someone's attention. And the last one that I find the most interesting is actually what we call the proximity sensor. And the way that this one works is, we all know how a cell phone works. Like, if you press it with your finger, it works great. If you use those just regular gloves that aren't touch gloves, it works really crappily. And that's what this one can actually do. So this one can actually detect innate objects. So if you put something on top of it, or if you press it with your glove, it would actually react. And a typical use case of this one could be to, well, like I mentioned earlier, it's so thin it fits in a crack. And the reason it's so thin is because of this exact sensor. Because you can fit it in the crack of any door or window, basically. Our CEO actually walked around with a tool in his pocket for months. What's it called? A thickness gauge, one with blades of different thickness. And he figured out that it can't be thicker than 2 millimeters. That's a physical design constraint that we can't go thicker than that. And there's no magnet or anything needed. Just put it in a door or a window and it just works. So, of course, this is only part of the solution. So, how does it connect? Like, what does it do? How does it fit into the bigger picture? Well, we have this thing that I put here, and it connects our sensors to the cloud. So we call it the cloud connector. And the way that this works, or how does this work? How does these sensors communicate with the cloud connector? Are we using Bluetooth? Are we using Zigbee? Are we using Wi-Fi? Actually, we decided to create our own protocol. If you're cringing a little bit inside, then that's a good thing. And I will actually talk a bit in detail of why we decided to make our own protocol instead of going for a standard protocol a little bit later in this presentation. And it also connects to the cloud, and how does it do that? Well, actually, you just plug this one in, and it will instantly connect to the internet. And the way this works is that you're essentially getting a cell phone. So it has built-in cellular connectivity, and it's powered by this, just by a regular wall plug. So you can just plug this in anywhere, and it will immediately detect any data coming from the sensors. So you plug it in, you press your sensor, and it's sent to the cloud, and it literally just works. And also, if you plug in more than one, it will also just works when it comes to roaming. So you can actually just take the sensor and walk between the two, and it will always pick the best one. And what's really cool with this is that it really means that installation just makes sense. You can literally just find the more or less best place where you have a wall plug, which can be along the floor or in the ceiling, depending on where you are, if you're in a store or an office. And you just plug it in, and it will automatically detect any of the sensors that are within range. And the sensors, well, they come with an adhesive on the back. So you just remove the adhesive. Like I said earlier, it weighs 2 grams. So no matter where you stick it, it's going to stay. And I mentioned a few use cases earlier. Some other use cases could be that you could fasten it underneath a fire extinguisher. So if someone would steal the fire extinguisher, you would get notified, or the heart starter kit, for example, or if someone's using the emergency exits. So there's tons and tons of use cases. What I've tried to illustrate here is actually measuring temperature basically at everyone's desk. So instead of measuring temperature in a big open landscape, you're measuring temperature in one place. You're actually measuring temperature where the people who are perceiving the temperature are sitting. So this is something that we see a lot of developers working with, actually. So, and like I mentioned earlier, if you find out that you have a bigger area that you need to cover than you can do with one cloud connector, you could simply just attach another cloud connector. And it will just seamlessly pick up the sensors that weren't connected before. Okay, so I've talked a bit about the sensor, and I've talked a little bit about the cloud connector, but how do you actually get the data? And this is actually really straightforward, so I'm going to try to do a live demo here today to see how you can do that. So 1 second here. So the way you do this is that you log in to your account in our cloud solution that we call DT Studio. And this is essentially kind of a developer platform. And you can use this to create service accounts. You can use it to grant access. You can use it to kind of browse your sensors here. And you can also just use it to see if something's happening. Like you can see that I'm clicking this one right now here. Or I'm clicking one of these. I think they support it too. Actually, it's a little bit crappy cellular coverage in here, so yeah, we'll see how it works. I will set up the data connector. So the way you do this is that you simply go to data connectors, and you say that you want to set up a new one. And this is a HTTPS push data connector. So it will simply push whatever sensor data to whatever endpoint that you specify here. And I'm going to use Dweet today, which is essentially it's an open free service that can be used to you can just send anything to a unique name here, and it will show on this address if you look it up in your web browser or similar address. I'll show you how it works. And I'm going to send only touch events. There's a few features I'm not using today, like you can actually sign this message with a secret, and you can do some other configuration here. But essentially, this is it. So I only filled in the URL and specified that I only want the touch events. So save data connector. We can take a look here. And I can actually just press a few of these sensors. We can refresh and see the result here if there was some events sent successfully. No, of course not. The demo effects. So let's see here. I'll do some live diagnostics as well. Okay, now it looks like it's actually sending something. Oh, cool. Well, we got 2 events through. So let's go to Dweet, like the chef. I've prepared it here. So this is a website where you can look at that same unique name here in real time. And you can actually see the JSON that's being pushed. So if I press it here, yeah. So you can see that it detects these button presses from these sensors. And this is the format that you will get all of our different events on. And of course, instead of using Dweet, this would be your Lambda function, cloud function, or however you like to ingest your data. So that's a little bit about that. Let's see. Oh, sorry about that. Yeah, right. Okay. So you got this sensor from us, you got this kit. This is a small IoT device. So you Google around a little bit, Google, Amazon, Azure, IoT. See where I'm getting at? Well, you're bound to find some solution that's, kind of named something like this. And I just want to mention a few words about these. So these are essentially trying to solve the problem of managing devices for you and doing configuration, firmware updates, identity management. They also often offer some type of analysis, maybe stitching together time series when you have missing data, doing some light analysis. But often the analysis part is just another product that they have wrapped in some IoT name. And if you're creating some type of cloud service, and you are also owning the product, the sensor, the device, then this is exactly what these services are for. When you own the cloud side and you own the device. However, of course, all of these companies, they're selling these services to everyone. So I just thought I'd just mention that while it's possible to integrate anything into these, to just kind of shoehorn the data in there, I just wanted to say that if you don't own the device, then there's a very high probability that you won't be able to utilize a lot of what they have to offer here. So this is kind of a solution that we could use who make the devices, but it's a lot less convenient to use, I would say, when you're integrating with platforms that already have kind of native push APIs. So what should you do? Like, how should you integrate with your platform? Well, I mean, what would you normally do if you wanted to integrate some social media or if you wanted to integrate some weather service? Well, of course, you would simply use the standard toolbox that you have. And I'm not going to say, what's wrong or what's right to use here. It's just that what I'm trying to convey is that there is really no reason when you're working with a platform that is already trying to abstract away all of those challenges related to IoT products, then there is no reason to use an IoT product on top of that. So you already know these tools. And I mean, if we're sending the data in a format that you don't like, and I mean, that's a really common integration problem. So you can just transform the data and you can put it inside any database or event queue or pub subtopic that you want. So it's really, really easy to use. And I just thought I'd mention also, so it's a little bit, you might be thinking that this is a little bit like a webhook. But webhooks they communicate in the same way, but webhooks are very often associated with fire and forget. And the way that our integration hook here works is actually we send an event over to you with the data from the sensor, and then we count on you saving it to a database or persisting it into a queue or a topic before you return 200 OK to us. Because we don't remove this event from our internal queue in your integration before you send 200 OK on this specific event. So that means that even if your services goes offline for a little bit, I mean, then your services, they're not going to reply back with 200 OK. So you're actually queuing them up on our side, and we will deliver them as soon as your servers are back upline again. So it's at least once guarantee. The other thing is that we don't wait for these kind of push, for these HTTP REST post calls to be finished before we send another one. I mean, it scales really well. So if you press this and you press it twice, then you will actually create 2 post requests in parallel. And this is, of course, to minimize the latency. Okay, so when I made this talk, I was thinking that I should mention some of the more exotic, eccentric, I don't know, product design decisions that we made when we designed this product. And well, one of the things that we decided to do was to design our own integrated circuit. And to be honest, Norway has really pioneered some of this area. So, for example, there was a few Norwegian companies that within IoT made it possible to reduce the size of radios from, credit card size PCBs, these green boards with components, tons of components, and you needed a lot of radio frequency expertise to design them. They managed to shrink them into these tiny, tiny integrated circuits, which are now used everywhere today. So there's definitely a legacy here, and a lot of our employees are actually from that type of background. But even though we had this legacy, it was still not enough. It was still not low power enough. And designing an integrated circuit is quite different from designing in say, an agile process. I would say it's kind of the opposite of designing in an agile software process. First of all, it's a huge waterfall model. Like, you spend a lot of time designing, you spend a lot of time trying to theoretically verify that it's working fine. And then when you actually want to produce it and you press the button, it can cost millions. And not only does it cost millions when you press the button, you'll also have to wait several months before you actually get the result and know that it works. And you get it back, and you find this tiny, tiny bug. You just want to go from version 1.0.0 to 1.0.1. Tough luck. That's another few million. That's another few months of development. And this is really typical in the integrated circuit industry. So before I dive into why, I'm going to talk a little bit about wireless battery-powered sensors in general and how they work. So typically how they work is that they have an active mode, and this is where they do everything. Like, this is where they measure using onboard sensors. This is when they send radio packets. It's when they do all kinds of internal processing, maybe post-processing of the sensor, and so on and so on. And then they have some type of sleep mode where they don't do anything, and then they wake up when something happens or on a timer. So how does this relate to power consumption? Well, all of these run on a battery, right? And if you pick up a battery in the store, you'll find some type of mAh in the number there. And this stands for milliamp hours. And that number there is how much capacity this battery has. It essentially means that if you are drawing 600 milliamps of current from this one, it will last for 1 hour. If you're drawing 300, it will last for 2 hours. Very simplified, but that's more or less how it works. And you have a fixed amount. And when you're doing a product, you have certain constraints. Maybe you have cost constraints, fiscal constraints, and you have a budget with regards to money. This will set the budget with regards to power. What can you do with your device with regards to power? So how do you calculate power consumption? Well, the way you do it is that you integrate current over time. And if everything pulled the same amount of current, this will essentially be this square here. So the grand total will actually be the area of this square. And the way that you calculate battery lifetime then would be that you divide that number, 600 milliamp hours, with the area of this, or the average. So then you would get the battery lifetime. But of course, it doesn't look quite like this. It looks more or less something like that. Actually, it's even more skewed. Very often, the sleep power, I would say, very, very often, the sleep power is something like 1,000 times lower than the active power consumption. So while we might want to spend all the time we can in active mode from like a functional point of view, because there you can do anything and you can do it quick, low latency, you can't stay there because of the power consumption. You would have, 1,000th of the battery lifetime almost than you would have if you sleep. And this is also, for this reason, this ratio between being awake and sleep is very, very skewed. So it doesn't look like this, like what I'm illustrating here. And it doesn't look like that. And you don't sleep, twice as long. You sleep a long, long time in relation to how often and for how long you're awake. So typically you're awake for a few milliseconds, just enough to get the job done, and then you sleep. Until you need to wake up again to, fulfill that minimum requirement you have of functionality on your product. And while this is 1,000 times more, it consumes 1,000 times more power when it's in active mode, remember that I said that you add up the area underneath the line here to get the power consumption. So if you add all of these up, what you'll find is that even though the active mode consumes 1,000 times more power, you will actually be spending a lot more of your power budget in sleep mode than you will do in active mode. Actually, even if you spend 99.99% of your time in sleep, sleep usually still constitutes about 95% of the average wireless battery-powered sensor, while the active mode may be around 5%. And so this is pretty crazy. And so given that this is more or less how it looks like independent of product, and you have a fixed battery, you can't do anything about the size of the battery. I mean, in a perfect world, you can just double the capacity of the battery, and of course you would get double the lifetime. But often because of physical or cost constraints, you don't. Actually, when I worked at TI, I worked with this really cool next generation wireless product. And it was using a lot less power consumption than the previous generation. A lot of our customers, and the developers, they weren't excited about the fact that they could get more battery lifetime. They were actually more excited about the fact that they could shrink the battery and get the same lifetime. So usually working with the battery and doubling the battery is not an alternative. So there's about 3 different ways that you can improve on this. So in the active mode, you're actually running your code that you've written. So, here you can actually spend some time to figure out if you can, tighten some loop somewhere. You can maybe interact more with a more low power sensor. Maybe you can send over your radio with a little bit less output power, so you're consuming a little bit less energy. So you can get this active power consumption down. But you have to remember that what I showed previously is still true. On a normal wireless product, a battery-powered wireless product, you would only be about 5% of your power consumption would be in this active mode. So you're only improving on that tiny 5% fraction. And the second maybe intuitive way that you might go to get more battery lifetime is that instead of, say, reporting a temperature value 2 times per hour, you report it 1 time per hour. This actually means that percentage-wise, you're spending less time in active mode. But of course, I mean, if you report half as often, do you get twice the lifetime? Of course not, because you're still spending all of this time in sleep mode. So if we really want to do something about this, we really want to get substantially better lifetime over a fixed battery, then of course what we need to tackle is the sleep. And this is really tricky, because in sleep mode, none of your code is running. It's actually not really doing anything except, well, nothing really, but it still costs you power. And here you're typically at the mercy of the microcontroller vendor that you picked. Like if you picked Silicon Labs or Nordic or Texas Instrument, you can look in their database, a PDF online, and it will say right there, active power consumption, X amount of milliamps. And yes, that one you can do something about by coding smarter and so on. But then it will also say sleep power consumption. And that's like a constant. You can't do anything about that, really. So what do you do about it? Well, if you're a little bit crazy like us, you design your own integrated circuit yourself. And this integrated circuit is this tiny, tiny, tiny thing inside of this tiny, tiny, tiny thing. And given the physical constraints that we had and the cost constraints, and the 15-year lifetime constraint that we more or less put on ourselves from the start, this was the only way that we could even build this product. So by designing this, we essentially reduced the power consumption in sleep so much that in this graph, you would barely be able to see it if you could see the area. But to put it in maybe a clearer way, if you compare it to how much power you would draw without it, then we reduced the sleep power consumption significantly. And you can see this in a couple of different ways. One way you can see this is that with the integrated circuit that we designed, we can now, over the same amount of time as before, we can do a lot more. So let's say that we found some way to do 15 years before, but only by measuring once a week, we can now do 15 years and measure once every 15 minutes. Or you could see it the other way around, and you can see it as if we would decide from the start, before we design the IC, that we want to measure every 15 minutes, then maybe we could measure every 15 minutes for a year. But after we design this integrated circuit, we can measure every 15 minutes on the same battery and get 15 years of battery lifetime. So that's why we created our own integrated circuit. So what about this custom protocol of ours? Well, I have to admit, when I had my interview when I was about to start at Disruptive and I found out that we were designing our own protocol, I was kind of thinking, like this XKCD. So why didn't we pick one of the huge standards out there? Well, to be honest, it's because we started by defining the product, how we wanted the product to work, how big it should be, and so on. We did not start with the assumption that we need to use one of these protocols between the cloud connector and the sensor. And then we kind of went from there. And don't get me wrong, I love standards. I love being able to take my phone to China and it still works. And we actually have a lot of experts inside of our company, people who have worked on the Bluetooth stack at Nordic and who have worked at the Zigbee stack at Scilabs. So we've taken a really, really hard look at all of these standards. And to be honest, if we found any one of them, if any one of them would have worked and would have ticked all of our boxes, we would totally have used it. Unfortunately, it did not. So, and why is that? Well, the first reason, there's really two good big reasons at least, and the first one is overhead. What if I asked you to design a sensor, a Wi-Fi sensor that needed to detect if a door was open or closed? And you'd maybe be thinking and designing this, and maybe you'd pick MQTT, or maybe you'd pick HTTP. And I mean, it's over Wi-Fi, right? So why not use internet technology? So, but the thing is, when you do this, is that from the get-go, you're incurring the overhead, let's say HTTP, you're incurring the overhead of HTTP over TCP over IP over Wi-Fi. And let's say you're using JSON. You have a file format as well. And if you're using JSON, you're most likely sending data in clear text instead of binary. So before you even start, you have all of these extra bytes. And what I didn't mention before is that in this active power consumption, the vast majority of that active power consumption is actually from the radio, normally. So what that means is that for every single byte you're not sending, you're saving power. And how much information do you really need to represent that a door is open or closed? Maybe around 1 bit. So this was one of our major focus areas. How do you send 1 bit of data as reliably as possible using industry standard encryption with as low overhead as possible? So this was one major focus of why when we designed the protocol, and one major reason to why we did. The other reason is because we wanted to design a system that has seamless roaming and end-to-end encryption. And the way that this works is that when you design a gateway, or when you design a protocol that communicates between a device and a gateway, you essentially have 2 dominating typologies or models. One is more or less like Wi-Fi. You have to know the SSID and you have to know the password. And if you go from home to your office or to a cafe, you will need to find out the new SSID and the new password. The second model is what your cell phone use, what the cellular operators use. So when you're on your phone and you're walking up Karl Johan towards the castle, you don't need to put down your phone and log into a new network first when you get to Stortinget and then when you get to Nationalteatret. And the reason for this is because all of the cellular operators implement something that's called seamless roaming. And well, we frankly just thought that there's only one of these models that really makes sense, so we went for the cellular operator seamless roaming model. And one of the reasons why we could do this, and one of the reasons that cellular operators can do this, is because they are in control of the entire infrastructure. Their responsibility, their protocols, doesn't end, it doesn't terminate at the gateway. It actually goes all the way to their backend. And that's exactly what we did when we designed our protocol. So what I mean here is that the cloud is a first-class citizen in our communication stack. It's in fact essential for us to be able to do what we do. It's why we're able to have end-to-end encryption between the sensor and the cloud. And we're still able to roam between cloud connectors seamlessly. So, and by end-to-end encryption here, I really mean it. Like, if you were able to compromise this cloud connector or any cloud connector, there is no way that you would be able to glean insight about the data that the sensor is sending. And of course, this is totally transparent to the integration with you guys, with your servers. So we take care of the deduplication, the encryption, decryption, and so on. And this is so from your end, from your cloud function, you will simply just every time I press this button, no matter if it's one cloud connector or several cloud connector, no matter if the sensor is mobile or if it's stationary, you will simply just get an event. And you will actually also get the metadata about what cloud connectors can hear your sensors. So if our integrated circuit is at the core of our sensor, maybe I should tell something about what's at the core of our cloud connector. And well, Docker adoption among cloud developers in general, or I guess PC developers, anyone really, is more or less universal. So we extensively, of course, use this in our cloud solution too. Actually, at NDC last year, one of our cloud architects were, maybe that was in Trondheim, were talking about how we use this together with a microservice architecture in our cloud to make our cloud. So I mentioned cloud developers and PC developers because embedded developers take a little bit more time to adopt anything. And but eventually, we adopted this too. So what we do is that we run a service called Resin.io, which is embedded optimized OS that runs an embedded optimized Docker-compatible runtime, small user space, systemd based, and of course a kernel. And this is available for a lot of the popular embedded development kits out there. And what we do is that we simply distribute our embedded software to our cloud connectors via a standard Docker containers. And it's managed by a supervisor on board. And this supervisor also comes with some really nice benefits for embedded devices. So as the previous speaker in this room said, when you have a cellular subscription for IoT, you typically get something like 10 megabyte or 50 megabyte or 100 megabyte. You get very, very, very little data. And this is super important. So it's super important to keep the data down. And one thing that Resin actually does is that it compresses the containers, so you're only sending the diff from container to container. So this can make pushing updates consume very, very little data. And of course, this just makes the way we work with this embedded software so much easier. We're essentially just distributing it as containers, like I said. So when you're it the environment variables that the container is exposed to, you're essentially just changing the environment that the device is exposed to. So it makes managing these really, it makes it a breeze. So that's a little peek under the hood. I hope that you've enjoyed that. I also hope that I convinced you, at least a little bit, that sensors can really help with improving the user experience outside the screen. And really the question at the center of all this is, of course, would knowing more about the real world actually help you add value to the user experience? And if the answer to this is yes, then this is exactly where sensors shine. That's me. Thank you. I would love some Q&A, if possible. If we have motion sensors, what do you mean by motion sensors? Do you mean like passive infrared or? No, not at the moment. We are only releasing 3 sensors to start with: the touch sensors and the temperature sensors and the proximity sensors. Of course, when you look at these sensors, the first thought is, about the sensors we don't have, almost independent of who you show these to. And we have some really cool things on our roadmap, but that will be after release. More questions?
What about applications to home?
Yeah, sorry?
What about applications to home, like Z-Wave, Raspberry Pi, like you have a sensor for the door.
Yeah.
If I open the door, the light should turn on, something like that. Integration with other devices.
Yeah, so it's a really good question, actually. And I think that when you say something turns on, I guess one thing that's implicit here is that we don't have actuators. We only have sensors. And one reason that we focused on sensors is simply because we think that there's going to be a need for a lot more sensors than actuators. And the way that you would typically integrate our sensor solution with another actuator solution or another sensor solution, is that you would simply have them talk cloud to cloud. And that's something that we think is the future. So that's how you would integrate it. Yeah.
Yeah, so what about you mentioned standards and so the HTTP push JSON message that you send, is that some kind of standard or are you using your own format?
Yeah, it's a really good question. If we're using a standard format for pushing our data when we do integration cloud to cloud. So that's actually an API that we've designed ourselves. And actually something I can brag a little bit about because we've had a lot of customer feedback that, that they found our REST interface to be kind of like what they actually exactly what they expect from the REST interface. That is the same terminology that I'm talking to you today is actually prevalent in our API. You get what you expect. You don't get too much information, but you don't get too little information. It's, but it's not a standardized format. If other than of course that we're using standard HTTP JSON. Come on, tricky questions. Non-tricky so far. Yeah, over there. Yeah, very good question. So the main difference is that during manufacturing, these are all flashed with an asymmetric, or several actually, asymmetric encryption keys. And when we ship these out to you, what happens is essentially that the encryption keys in this sensor, the other end of them, so to say, are allocated to your account. So even if the data arrived via your neighbor's cloud connector, there is no way that no one else could see your data. Good question. Yeah, here? Yeah, so we have created some processes around that. What we recommend right now is that when we ship a sensor to you, you kind of have them in a special type of project. Inside of this Data Studio that I showed you, this developer console, you can have several projects. And the ones that you get when we ship them goes into a special inventory project. So what we recommend is that when you move a sensor out to a real installation, you move them out of this inventory project. So that means that when you are doing the installation, you can actually just touch a sensor because you can assume that since you're only listening to installation sensors that are not installed, this is going to be the only touch that's happening right now. And that way you can actually identify the sensor. And that's something that we support natively in our developer console as well as through our API.
It's working with the touch sensor, but how can I identify a temperature sensor?
Yeah, it's an excellent question. So all of the sensors actually support that. Yes, here? Yeah.
So what about the design for user experience? Did you use some focus group or how did you end up with this? Like how did you verify that this is meeting the expectations of it?
Yeah, well, what we did was actually that we created a sensor that, it looked exactly like this sensor. It had the same physical appearance, but we made it before we had the integrated circuit. And we essentially used this, so that meant that we had a sensor that had very, very, very bad battery lifetime. But it also meant that we could develop it rather quickly, and we also kind of, jerry-rigged it together at home, like with melting putty at home instead of big machines, and kind of tried to make it look good. And we had something that looked kind of like this. And we used that to verify our assumptions, a lot of our assumptions, I should say, at least. Any more questions? Sorry, my connotation there was like, I don't want any more questions. Any more questions, please? Okay, well, cool. Thank you so much. I actually have some, plastic dummy sensors here. So if you just wanna, if you want to, you can actually grab one of these and take one with you home. It just shows kind of the dimensions of it. You can just drop by me later here. Thank you so much.